Hello and welcome. In this video, we are going to take a look at second-order differential equations. So we tend to live in a second-order world, and so it's not uncommon to see second derivatives in real-world phenomena. So most commonly, you might have seen second derivatives in applications involving acceleration of some sort of body over time, whether that be a car or a bike or some sort of object floating through space. So before we get started in this, let's motivate the development of a model with just a little bit of algebra first. So let's say that we were faced with this second-order homogeneous constant coefficient linear differential equation. The second derivative minus y equals 0. Now let's for a second observe that the reason this is called second order is because the highest derivative present is the second derivative. Constant coefficient is something that is convenient for a differential equation. Notice that the coefficients of all the terms involving y are constants. Here we could place a 1, here we could place a -1. And so that explains the constant coefficients. Linear because we have y to the first power, so therefore our classification system works again. So if we look at this equation and we wonder, well, how do we go about solving this? You can't really use separation of variables in the same way that we were able to with first order. But if we begin to think about what this equation is saying, it lends us insight into what the solution might look like. So here we're saying, and I'm going to go ahead and use the y prime prime notation here. And the reason I'm going to do that is just to save on having to write the second derivative. So if I add y to the other side, I see that what I have to satisfy in order to solve this differential equation is that the second derivative of y has to equal y. So the second derivative of y must equal y. Well, we begin thinking a little bit about what functions we know whose second derivative equals the original function that we started taking a derivative of. Well, I can kind of begin exploring this to see if I can guess any functions that would work here. And I can say, well, geez, let me think of some candidates. And I like to use the word candidates because these are not necessarily solutions, but these are just my guesses. So you can think about these as educated guesses. Now, I'm going to be really sort of out there right now, and I'm going to say, well, what about something like e to the t plus t squared? Well, I have to make sure that in order for it to solve this equation, I have to make sure that the second derivative of what I pick as my candidate is the same as the original function. Well, I take the derivative of this, and I see that it's going to be e to the t plus 2t. And now if I take the derivative of the derivative, I get e to the t plus 2. And we notice the relationship between y and the second derivative, these two functions, we see that they are not equal to one another. And therefore, since they're not equal to one another, then this means that this is not a valid candidate solution. So I have to begin thinking, if I'm going to be strategic here, not just guess, I have to guess things that I know that when I take their derivatives, eventually I get the same function back. Well, another guess might be an exponential, because here I even see that an exponential, when you take its derivative, you keep getting the same function back, right? So if I take the first derivative and I see that, I take e to the t, and now y prime equals e to the t, and y double prime equals e to the t, I see that that does, in fact, work here. So the reason I see that that works is because these two are equal, and I want to make sure that they're equal before I claim that they are, in fact, solutions. So, our solution here is that y equals e to the t is a solution. Now, you may not see this at first, but you can keep playing around with this. Unfortunately, things like y equals e to the 2t won't work, anything where the exponent is not related to 1, because when we take derivatives of e to the 2t, we have to use the chain rule on the exponent and multiply it by the derivative of the exponent. And so by the time we take the second derivative, we get 4 e to the 2t, and clearly these two are not equal. Now, one other solution that would work is y equals e to the negative t. And the reason that will work is because when I take its first derivative, I get negative e to the negative t, or negative 1 e to the negative t. And if I take the derivative of that, now I'll get negative 1 times negative 1, which is positive 1. And we see that these two are, in fact, equal. So here, we do have equality. And so y equals e to the negative t is also a solution. Now, to keep these distinct, because I want to refer to these as different solutions, so perhaps I'll call this one y1, and this will be y1, y1 prime, y1 double prime, and we'll call this y2, and the y2 prime, y2 double prime. That way I see I have two solutions. Now, one interesting thing that we'll notice is that with second-order differential equations, we will have two solutions. And this is a very common feature. Let's take a look at another example before we delve any deeper into some of the building blocks here. So here we notice that it's almost the same equation, but we have to ensure that the second derivative is equal to 4 times the original function. Now clearly e to the t won't work because its second derivative is exactly the same as the function we started with. E to the negative t won't work as well because it is exactly the same as what we started with. What I have to ensure is that y double prime is 4 times bigger than y itself. And if I look at one of my guesses here, or one of the things I was playing around with, if I chose y equals e to the 2t, then its second derivative, we've already calculated, is 4e to the 2t. And check this out. If I now substitute these in to see if they're equal, and by the way, checking second order solutions is exactly the same process, is that equal to, question mark, 4 times y, which is e to the 2t? Well, 4e to the 2t is in fact equal to 4e to the 2t, and therefore y1 equals e to the 2t is a solution. In fact, you could put any coefficient in front of e to the 2t. For example, if you put 7 here, then this number here would just be 7 times 4, which is 28, and still that would be 4 times bigger than the original equation. So any constant out front will work, but the exponent of 2 is necessary because that's the only way I could develop new coefficients. The original 7 here just follows along all the way down, and it never changes only by virtue of the fact that it gets multiplied when we take derivatives. So the next question is, would there be any other solutions? Well, naturally, if I want the second derivative to be 4 times bigger, I can also look at e to the negative 2t, because when I take derivatives, again, it requires 2 derivatives to get something to be 4 times as bigger as the original function. The first derivative pulls the 2 down once, the second derivative pulls the 2 down again. So let's see if this one works. Y prime equals negative 2e to the negative 2t, and y double prime equals negative 2 times negative 2, which is 4e to the negative 2t. And to just check my work, I have to see, does the second derivative of y equal 4 times y? And, well, if I substitute in what y double prime is, it is 4e to the negative 2t. And does that equal 4 times e to the negative 2t? And you can see that clearly these are going to be equal on both sides. So this solution here, which I'll just call y2, gives me a second solution. And once again, you see that up here, I kind of mentioned that, well, second order differential equations are each going to have two solutions. And we'll see shortly why that is. But for now, it's purely speculative. E to the negative 2t is a solution. Okay, well, right now, the fact that we have two solutions may raise a question in our mind as to, well, what do we do with the two solutions? Which one do we use? How do we use them? Do we use them both? Do we combine them in some way? And in short, the answer is yes, they do get combined, and you use all the solutions to form a general solution. Okay, so what can be said generally about this type of differential equation? So notice that what we changed, one of the things in mathematics is that we often want to observe patterns. And the only difference between this equation and this equation down here is they're both subtracting the second derivative in the original function. The only difference was the coefficient in front. Well, I'm going to make the argument that I'm seeing a pattern here, that if this had been y prime minus, 9y equals 0, then I would be willing to bet that e to the 3t and y2 equals e to the negative 3t would be solutions. Because in this case, this is suggesting that the second derivative has to be 9 times bigger than the original function itself. Well, if I take the second derivative, remember the first derivative puts that first instance of the 3 down as a coefficient, and then the second time you differentiate it, it becomes 3 times 3 e to the 3t. So the square of this number right here has to equal the coefficient that we want in front of the 9. And same thing will happen here. y2 double prime will be negative 3 times negative 3 e to the negative 3t. So I'm going to hypothesis is that if I had y double prime minus some constant, we'll just call this, what do we want to call this? We'll just call this minus a times y equals 0, we would be willing to guess that y1 equals, what was the relationship between the 9 and the 3? The relationship between the 9 and the 3 was that we would expect the exponent to be the square root of that number, like so. And y2 would equal e to the negative square root of a times t. Now, t is not in that square root, so the important detail there to note, because these can often start to look the same, but you have to be really cautious. And let's just make a quick proof here. Well, if in fact these are solutions, that means y1 equals e to the square root of a times t. Its first derivative would bring that first instance of the square root of a down. So square root of a, e to the square root of a t. And then the second derivative would bring the square root of a down again, and you'd have square root of a times square root of a, e to the square root of a times t. Now that's going to give us square root of a times square root of a is just a, e to the square root of a times t. That is all great. Now we just have to check that it actually satisfies the equation up here. So does y double prime, or I should say y1 double prime, minus a times y1 equals 0? Now we could have also said, does y double prime equal ay? That would have been fine as well, but putting it into the original equation, I see that y1 double prime is a e to the square root of at minus a times y1, which is e to the square root of a times t. And I can see that those are exactly the same, and therefore they will cancel out and give us 0. And a similar argument can be made for the negative square root. The intermediate first derivative, by the way, is not a derivative that we actually use. Right? That first derivative is just a stepping stone to get us to the second derivative. The first derivative has not come into play yet in these second order models. So we've proven for y1, similar proof would hold for y2. So we've just solved a whole kind of family of differential equations without having to do very much calculus, just a little bit of differential calculus.